So today I will speak of quantum mechanics and its relations to Buddhist interdependence. The first thing to understand with quantum mechanics is that, for 100 years now, almost 100 years, it has been taken as a strange theory, a theory that is not non-standard, a theory that creates difficulties, puzzles, enigmas, paradoxes, and so on and so on. But, now, the more we think about that, the more we realize that the reason why there seems to be so many difficulties and paradoxes with quantum mechanics is that we try to fit this theory in a philosophical and even metaphysical framework which is inherited from Aristotle and from all the, the main trend of Western philosophy. The idea, as I told you yesterday, is that quantum mechanics, since it is a physical theory, it's a scientific theory, it should give us a picture of the world and, if possible, a faithful picture of the world. We would say even that quantum mechanics should give you a view of the world, even almost in the metaphysical sense. But maybe precisely all the reason for so many difficulties in quantum mechanics is that quantum mechanics affords absolutely no view of the world, no representation of the world, nothing like scientists hoped for. And, I quote here Richard Healey. Richard Healey is a very important philosopher and interpreter of quantum mechanics. He has been well known for so many years for very serious and very precise work on this topic. And recently, Richard Healey has completely changed his mind. He has understood, finally, that quantum mechanics doesn't afford a view of the world. That's very simple. So let's read his quote, so the quote is drawn from a book called The Quantum Revolution in Philosophy. And the title is interesting and strange, It's not the quantum revolution in science, it's not the philosophy of quantum mechanics, it's the quantum revolution in philosophy. Richard Healey means that quantum physics forces us to change completely our minds about philosophical issues. So here is the quote. The main barrier to understand quantum theory is not our inability to imagine the world it describes, but the presumption that it be understood as describing the world. Okay? So the difficulty is not that we don't know exactly what is the world, how the world described by quantum mechanics looks like. No, it's just that we have a prejudice that quantum physics should describe or represent the world, and it doesn't. Very simple. Quantum physics is no view of the world. That's a slogan, okay? Okay, now another point I want to display here in this talk is that, quantum physics might be a paradox also of the history of Western philosophy. Because, as I told you yesterday, the whole trend of Western philosophy for 2,500 years has been to explain the essence of the properties of things, the ultimate causes of things, and to represent nature for this sake. And finally, at the end of this push towards representing nature and towards understanding, I would say, the own being of things, here is a theory that is extremely powerful for prediction, for technology, And yet, it says to all this trend of Western philosophy, no, you cannot do that. You cannot do what you wish to do, namely elucidating the own being of things. The more your theory is powerful, the less it says something about the own being of things. That's the lesson. That's really, I think, a very big lesson. I must say also, usually in many books you find about quantum mechanics, popular books, you find, that these strange features of quantum mechanics, when it is deemed to say something about what is the world in itself, the strange feature of quantum mechanics maybe say something wonderful, surprising, non-standard, almost science fiction about the world. There are books about quantum healing, quantum medicine, quantum wonders, and so on and so on. And I really think it's completely wrong, because quantum mechanics doesn't say something extraordinary about the world. It says something extraordinary about ourselves, about our knowledge, about the limits of our knowledge. And it says something amazingly similar to the lessons of the deepest lessons of Buddhism, namely Madhyamaka, essentially. So I will show you this. So, when people try to compare science and Buddhism, not science and Buddhism, quantum physics and Buddhism, and you know that many people have done this, from Fritjof Capra in the late 70s to many others in between. So when they compare quantum physics and Buddhism, they tend to think that they will compare two views of the world. But in fact, what they should compare is not two views of the world. It's rather two of the most radical critiques of views that have been proposed in the history of human thought. Buddhism is more than a view of the world. The deepest lesson of Buddhism, I take it to be, the elimination of views by Nagarjuna in his Mula Madhyamaka Karika. And the deepest lesson of quantum physics is the same. Impossibility to give a view that is coherent, universally accepted, and approximately acceptable. Nowadays, there are, as you know, there are many so-called interpretations of quantum mechanics, but they don't agree between each other. So maybe the right interpretation of quantum mechanics, as Richard Healey, Chris Fuchs, and so many other authors say, is a non-interpretation of quantum mechanics, namely saying, no, it doesn't say you something about the world. Okay, so let's compare some sentences. For instance, Nagarjuna in his Mula Madhyamaka Karika. Emptiness is the relinquishing of all views. When you see what the best specialists of quantum mechanics have said, especially since the foundation of quantum mechanics, for instance, Niels Bohr in 1927, something similar arises. Quantum mechanics, he said, is a mathematical symbolism intended to predict probabilistically the outcome of experiments. Where do you see a view here? There is no view of nature. Quantum mechanics is just a mathematical symbolism for predicting outcome of experiments. Nothing beyond experiments, nothing strange going on in the world that might maybe explain the outcome of experiments. We don't know. We have no idea. And maybe it's wrong to ask even the question. Also, this sentence that is drawn from Tsongkhapa, statements which appear to reject all theses, namely all views are to be understood as intending a rejection of inherent existence. So rejection of views means rejection of inherent existence. It doesn't reject relative existence. It doesn't reject interbeing, as, for instance, Thich Nhat Hanh said. Now, what about quantum theory? In quantum theory, as you will see, properties, the so-called properties of particles, have no intrinsic existence. They are called observables, not properties. Observables means that they arise when an observation is made. You cannot say that they existed out there and we just realized by an observation that they existed. We don't know, here again. Maybe there is no meaning saying that. What we know for sure is that there are observables, namely that there is co-arising of something out of observation. No intrinsic existence of properties. Quantum field theory, also a more advanced branch of quantum physics, says that not only properties of particles have no intrinsic existence, but also particles have no intrinsic existence. You will see later, I will explain a little bit more. But clearly, not properties, no particles, what? Phenomena, observables, nothing more. People describe these kind of particles as observables, in terms of quantized excitation of the field. What is the field? What is the quantum field? You may wonder. Maybe it's something, some stuff, some inherently existing stuff? No, not even. Quantum field is just the name we give to the disposition there is for what we explore to make a phenomenon arise. Nothing more. We don't know, once again. We give names, but we don't know what the name stands for. Certainly, they don't stand for something inherently existent. Okay? Okay, so clearly here, as I told you, there is a remarkable parallel between I would say, the deconstructive strategy of Buddhism and the deconstructive consequence of quantum physics. You know the Buddha's parable of the arrow. When someone has an arrow, don't ask too much about the origin of the arrows, the cause of the arrow, the one who sent the arrow, and so on. Just try to extract the arrow to relieve the person. So don't ask too much about complicated stuff. And the Buddha, when asked about the origin of things, the destination of things, the deep nature of things, he usually answered by a noble silence. He was silent about the modes of reconstructing the past and speculating about the future. Okay. And of course, what I love most is Nagarjuna and his careful deconstruction of views. Each time there is a view, he shows that it is rationally inconsistent, and therefore the view is no longer possible. But not only the view is not possible, but the reverse is not possible either. The combination of the view and the reverse is not possible either. And the combination of the negation of the view and the opposite view is not possible either. This is called the tetralemma. You know that. Now, when you have said that, when you have deconstructed views and so on, what is left? You certainly know more about that than myself. But I think, to me, the lesson of this is that ultimate truth cannot be captured by a metaphysical picture, by a view. It cannot be expressed in words or even in mathematical symbols. So it has to be lived through. Okay. In quantum physics, many authors have reached similar conclusions. I have shown you Richard Healey with his wonderful sentence, but there are so many other authors. One of the first who was extremely clear about that was Asher Perez. He was a physicist. I met him several times. He was really impressive because each time someone said, there is a paradox in quantum physics, he just opened his eyes widely and said, no, I don't see a paradox here. It's just because you wrongly interpret quantum mechanics. If you don't wrongly interpret quantum mechanics, there is no paradox. So his strategy to interpret quantum physics properly was to suspend judgment about physical systems. Usually when you read the text of quantum mechanics, you say, you have a symbol, which is called psi. It's a Greek letter. And you say psi is the state of a system, a state of a system. This sentence that you find in every textbook of quantum mechanics and in every article about quantum mechanics is full of prejudice, full of philosophical, metaphysical prejudice. A physical system is not inherently existent. So it should not be named as if it were inherently existent. And psi is not really the state, as you will see, of anything. It's a tool that we use to calculate probabilities. So, according to Asher Perez, you should stick to what we do at the laboratory and what we see in experimental outcomes, and don't try to put on these symbols all the burden of 2,500 years of history of Western philosophy. You should not say, oh, there is a system, it's a hard substance existing intrinsically, and there is the state, a property that is inherently possessed by the particle or by the system. No, you should suspend judgment about these two things, about the system and about the state. And still, you can use quantum physics as a wonderful tool to predict and to make new technology. This old philosophy is not necessary for the theory to work, one, and secondly, it's it's a hindrance to understand it. So why stick to it? Okay. Zeilinger, Anton Zeilinger, maybe you know him. He is a very important and celebrated experimental physicist of the University of Vienna, and he has participated in many mind and life dialogues with His Holiness the Dalai Lama, explaining him quantum physics. And he has exactly the same ideas, by the way. So it was interesting because His Holiness could immediately connect with his ideas. So according to Anton Zeilinger, quantum mechanics is a theory of the limits of available experimental information. Okay? It's not a theory of particles, their properties, their states, and so on. No, it's just a theory of experimental information. And you can, here again, read quantum theory without any problem if you stick to this very modest, minimal interpretation. It works. Not only it works, but it's amazingly fruitful, as Zeilinger himself has shown in his laboratory. So now a little bit more, going a little bit deeper in what is quantum theory. And first, for the sake of comparison, I should start with classical mechanics. So yesterday I said some elements of classical mechanics, but here I will try to summarize and to show you the way it works. At the very, very lower level, quantum mechanics is essentially a mathematical tool for you to predict the position and the velocity of a material body at a later time if you know the position and the velocity of the same body at an earlier time. So you see, the use of classical mechanics is very simple. You have measured position and velocity at time 0, here, and you want to know position and velocity of the same thing at later time t. And you use equations, so-called evolution equations, either Newton equation or Hamilton equation, whatever. They are all equivalent, by the way. So it's a mathematical machine, so to speak, to transform coordinates, namely velocity and position at time 0, into velocity and position at time t. Here is the basic use of the equations of classical mechanics. And then you do a measurement, and you see that it fits with the prediction of the theory. For instance, you see the moon at a certain position with a certain velocity, and classical mechanics tells you, oh, in 1 year it will be there with this velocity. And here is the wonderful achievement of classical mechanics. The same, of course, for special probes, special vessels, as the Apollo vessel that went to the moon, and so on and so on. Okay, now this is just the mathematical skeleton of classical mechanics, but with it comes interpretations. What is very interesting is that in the history, there was not only one interpretation of classical mechanics, but at least two, maybe more. There was the interpretation of classical mechanics of the main author of classical mechanics, namely Isaac Newton. According to this view, the world is made of material bodies, intrinsically existent material bodies, endowed with position and velocity, and attracting each other by a force that decreases with the square of the distance between the bodies. Okay? So here is the picture. Bodies, they have intrinsic positions and velocities. They have the capacity, they have intrinsic masses also, and they have the capacity of attracting each other. Later on, in the 19th century, new theories of physics appeared, as you know. Two theories were really new in history. One of them is called thermodynamics. Thermodynamics is the science of heat that was used in order to build steam machines that were used in the 19th century. And the second important new theory of the 19th century was electromagnetism. Maxwell was the author, well, one of the main authors of the theory of electromagnetism. So what was common to mechanics, classical mechanics, thermodynamics, and electrodynamics? Only one thing: energy. Energy could be transformed from one form to another. For instance, if you had a steam machine, it transformed the energy of heat into mechanical energy, motion, and then motion could be transformed in a dynamo into electrical energy, so electromagnetism. Okay? So three things could be transformed in one another by transferring energy from one system to another. So the idea at that time was that material bodies were not so important, in fact, not fundamental. What was fundamental was energy, only energy. And so some people thought that, in fact, the world is made of pure energy. Motion is just an aspect of energy. And bodies, even bodies, are not really solid. They are just packs of energy, packages of energy. So here is a new view of the world, completely different from the other one, and yet completely compatible with the mathematical skeleton of classical mechanics. So you see, I think this is just an illustration to show you how much independence there is between the mathematical skeleton of a theory and its metaphysical interpretation. Metaphysical interpretation means what there is in the world, what there exists intrinsically in the world. So for the same mathematical skeleton, you can have many interpretations. But at that time also, in the 19th century, there was also a non-interpretation of classical mechanics. It was the so-called sensualistic positivist non-interpretation of classical mechanics, which was given by the Austrian physicist and philosopher Ernst Mach. Ernst Mach said, what there is in the world is only one thing, sensations, nothing else. So all your views about the world are just constructs out of sensations. In some way you could say all there is in the world, according to Mach, is lived experience. And you construct all views of the world from lived experience. So here you see, I would say, a deconstructive reading of classical mechanics, which is not a view of the world, but a non-view of the world. Maybe I would say a positivistic or idealistic view of the world, but it's much weaker ontologically than the view that the world is made of material bodies or made of energy. So you see, one mathematical skeleton and many interpretations, and maybe even one non-interpretation. The same, of course, for quantum mechanics. But, for quantum mechanics, it's well known that there are many interpretations. For classical mechanics, people don't usually know that there were so many interpretations. So what is quantum theory? In the history of quantum theory, people said, okay, quantum theory is a theory that describes motion that is performed by jumps instead of continuous motions. This is the meaning of quantum. Quantum means that motion is made by jumps, discontinuous jumps instead of continuous motion. Also, in history, for instance, Louis de Broglie have invented the idea that corpuscles can be piloted, guided by a wave. The famous duality between waves and corpuscles. Another important element of the history of quantum mechanics is indeterminism. Namely, you cannot predict a singular event with absolute certainty. What you can give is only its probability. Okay, now let's skip all this history for the time being, after I will come back to it, and just see how quantum physics works. What is the skeleton of quantum mechanics, just as I showed you the skeleton of classical mechanics. So the skeleton of quantum physics is this one. So you have a certain function psi. I don't say what it is for the time being. People say it's the state of systems, but I told you that this sentence carries the weight of 2,000 years of metaphysics. Instead, here I don't know what it is, but I know what it is used for. Okay? What is it used for, this function psi? It is used to calculate the probabilities of finding an experimental outcome. For instance, here you have in the lower part, you have an example of one of the simplest quantum experiments. It's called the Stern-Gerlach experiment. It's just, you have a magnet which generates non-uniform magnetic field, and then you throw a beam of radiation of a certain type across the field that is generated by the magnet. And then, strangely, you don't find a continuum of values, but only two possible values. So when you send something through this, sometimes it will land on the lower part, sometimes it will land on the upper part, but nothing in between. So there are only two possible outcomes of the experiment, upper or lower. Upper, I note plus, and lower, I note minus. So the function psi allows you to calculate the probability of finding something up, namely plus, or something down, namely minus. Here we are. Nothing more at this moment. This is the skeleton. It's not about, yesterday I said that Einstein said, don't believe what scientists say, just see what they do. So what they say is, psi is the state of a physical system or the state of a particle. What they do is completely different. They take this function psi, it's a mathematical symbol, and they calculate probabilities, nothing more, okay? So what they say is different from what they do. And probabilities of experimental outcomes, not probabilities of being something or being something else, just probability of finding a certain observation. Now, you have a second crucial element in quantum physics, just the same kind as in classical mechanics, an evolution equation. Namely, it shows you how to transform this function psi at time 0 into a psi function at time t. Then, from the psi function at time t, you can calculate probabilities for the same kind of experiment, because the probability changes with time. That's one of the crucial points. Okay? Now, you have calculated the probabilities for the two possible results at time t, and you do a measurement. And you remember last time in classical mechanics, when classical mechanics predicts values of position and velocity, you find exactly the values that are predicted. Here you don't find the values that are predicted for the same simple reason that there is no such values that is predicted. The only thing that is predicted is the probability. So how can you check that quantum mechanics does the right predictions? Only by doing many, many experiments and showing that the statistics of the outcomes plus and the outcomes minus is perfectly adequate to the probabilities that are afforded by quantum calculations. Okay? So here is the skeleton. But also, and a final point, when I do a measurement, I have usually one of the two possible values, either plus or minus. So here I say the outcome has been plus. Now, if you want to do a further experiment after this one, what kind of function do you use? What kind of function, psi, do you use in order to calculate future probabilities after the measurement, after the first measurement? Probabilities of future measurements after this present measurement. In order to do that, you don't have to take the same function psi, but you have to redefine psi to take into account the information you have gained by doing the experiment. you redefine the function psi. Okay? This sounds very abstract, but maybe some of you have heard of the reduction of the wave packet, the reduction of the state, something like that. People say a measurement suddenly changes the state of the system. And they are surprised. Why should a measurement change the state of the system? It looks absurd. The state of the system belongs to the system. It doesn't belong to the guy who measures. So it sounds strange when you read quantum mechanics this way, namely in the usual way in which you say that psi is the state of a system. But if you read that like I said here, it's very simple. Since psi is no longer the state of a system, the fact that the measurement changes it is no longer extraordinary. In fact, the measurement doesn't change it. What it changes is your expectations. Because now you have new information that you have to take into account in your future expectations. It's perfectly natural that information changes your expectation. Instead, it's very unnatural that information changes the state of an inherently existent system. Okay? So you see, if you change the interpretation, you immediately see one of the famous paradoxes vanish, literally. Not be solved, because there is nothing to be solved, just vanish. Okay, now I told you that in classical mechanics there were many interpretations, and in quantum mechanics there are also many interpretations. It's quite difficult to list all the interpretations, but maybe you could say that most interpretations focused on an attempt to understand the nature of psi. What is psi? What does it represent? And I would say, does it represent something? So this is my choice, my personal choice. Maybe it doesn't represent anything, but so some physicists said, okay, psi, which is the symbol that intervenes in the equation of quantum mechanics, is maybe or at least not is, but at least represents some sort of reality. Schrödinger, when he invented the Schrödinger equation in 1926, said exactly that. Psi represents a real wave, waving in the world, okay? Real wave. So psi represents reality, because according to Schrödinger, reality is made of waves, literally. But then he had to understand how it is that, there are appearances that look like not waves, but particles. So how could he account for that, since according to him, the world was made of waves? And that's the reason why he invented the concept of wave packet. Namely, if many waves interfere, there is a bump, and the bump of intensity of the wave can mimic the effects of a particle. So he had his purely wave-like interpretation, and he tried to mimic the apparently corpuscular appearances by means of his waves. So psi, according to him, is all the reality there is. But according to other interpreters of quantum mechanics, psi represents a wave, but this wave is not all there is. In fact, the reality is dual. It is half particular, half wave-like, okay? Half wave, half particle. So it's sort of combination. According to Louis de Broglie, as I told you, a particle was guided by a wave. So there was sort of surfing, as if you could say something like that. The particle was surfing on a wave, and it was guided by the wave. You will see just after that a little video that shows you that, with a wonderful little experiment that was done on the surface of water. But another possibility is that psi is not the representation of some sort of reality, but it's just a mathematical tool to calculate the probability of a particle being found here or there.
Quantum physics could not be explained. That we would just have to accept that we'll never know why things behave as they do down at the deepest levels of existence. But now, a growing band of rebel scientists thinks there may be a logical explanation for quantum weirdness after all, and new hope for revealing the ultimate truth of our universe. The trail begins here, with a drop of silicon. In his Paris laboratory, physicist Yves Coudet and his team conduct an amazing series of experiments. They are observing the behavior of silicon droplets bouncing in lockstep on a vibrating plate.
The liquid of the drop never touches the liquid of the substrate, so they're always separated by air film. And in fact, this is stable. You can keep the drop bouncing on the liquid surface for several days if you wish.
Using a camera that shoots 1,000 frames per second, Coudet has discovered that these droplets mimic behavior seen in the quantum world. And that shouldn't be possible, because the quantum world and the large-scale world play by two different sets of rules. Yet here we see a single droplet moving randomly like a quantum particle, but behaving like a quantum wave. If you watch this carefully, you'll notice that the wave appears to be guiding the droplet. In fact, the wave fields around the droplets develop a memory of the trails they have followed. Despite their random behavior, they follow a small number of paths. Again, this is eerily similar to the behavior of quantum objects. This runs so contrary to popular belief that at first, Coudet refused to believe what he was seeing.
In any physics experiments, you only see what you are prepared to see. Of course, this was very obvious that there was a memory, but it took us some time to realize that it was that we were observing, because you have to adapt to this new idea.
Perhaps most revealing of all, Coudet has reproduced the double-slit experiment using his bouncing silicon droplets. The mystery of quantum mechanics is, how can things like electrons sometimes behave like particles and sometimes behave like waves? Perhaps this is the answer. They are particles and waves. Of course, this system, though small, is not quantum.
Our system is not a model of quantum mechanics, but it is an association of a particle and a wave, and some of its properties are similar to the properties that are observed in quantum mechanics.
Coudet won't claim that his experiments show us what is really happening down at the deepest layers of existence. But this man will. To him, those droplets are more proof that the quantum world makes sense after all, and that reality really exists.
Here we are. So I think it's also interesting, this film, because it shows you two attitudes in physics. The one of Yves Coudet, the French physicist that was the author of the experiment, and the one of the American physicist at the end. So Yves Coudet just said, okay, I have here a beautiful model of some behaviors that are similar to the quantum phenomena. But the American physicists said, no, this is more than that. This is a model of what happens in the deepest layers of reality. Okay? So you have two attitudes, a modest attitude and a very ambitious attitude, I would say, very metaphysical. So, and I think, of course, I believe that the French physicist is right, not only because I'm French, but he's right because he understands, he's very lucid, he understands that his model is just a model of one possible interpretation of some phenomena of quantum mechanics, which is the so-called guiding wave model of de Broglie and David Bohm. Okay? But as everyone knows, these two models, so Louis de Broglie's model and David Bohm's model, with a guiding wave, only account for a few facts. Many facts, actually, but not all the facts of quantum physics. So if you have a good model of an interpretation, such as the interpretation of the guiding wave, you don't have a model of all of quantum mechanics, and even less a model of the deepest recessive of inherent existence of reality, okay? So we have to be modest, and I think the French author of the experiment was modest. So this is just to show you that nowadays also, there are people who believe they have the right interpretation of quantum mechanics, and the interpretation of quantum mechanics that maybe pictures the inherent nature of reality. But there are also other scientists who are on a completely opposite track. Namely, they don't try to find a model of the deepest recesses of reality, but they try to understand why it is that we don't have such a model, and that each time we do try to elaborate such a model, we land into difficulties, troubles, and paradoxes. And therefore, some physicists, now the trend is really rising very quickly, by the way, another set of physicists elaborated, I would say, a criticism of the interpretations of quantum mechanics under the name of quantum Bayesianism, or QBism, as an acronym. Quantum Bayesianism means that in order to understand quantum physics, we use a special theory of probability that was elaborated by a guy called Bayes in the 18th century. So according to this view, or this non-view, I would say, quantum physics is nothing else and nothing more than a particular kind of theory of probability. Probability of what? Probability of observations, here again. But beware, this idea that quantum physics is just a theory of probability can have also many interpretations. The first interpretation is that we use probability because we ignore what is going on below the curtain of appearances, so to speak. But another, this would be the idea of epistemic probabilities, namely probabilities because of lack of knowledge, statements of ignorance. But in fact, what the people of QBism say is not that we use probability because of ignorance of something inherently existent that goes on beyond the veil of appearances. What they say is that probabilities are used to guide us among observations that we cannot say that we ignore them because they only appear when we do the experiment. So we cannot say we ignore something that has not happened at all. We just have to guide our own action in a situation in which every observation arises with our action. It's what I was saying, I was telling you yesterday. So, in the standard quantum picture, for instance, you remember what I said. Or what I said is that, for instance, a quantum state, the psi, can represent a case in which you are uncertain. The outcome can be plus or the outcome can be minus. In the standard quantum picture, this undetermination is something that occurs in the world. The world is indeterminate because the state that pictures the world is itself in a state of superposition. So here is the standard quantum physics. The world is indeterminate. It doesn't know whether it's plus or minus. But in quantum Bayesianism, it's not the world that is indeterminate, it's us. It's us. Us who are not only uncertain about something that occurs in itself in the world, but indeterminate about something that we will trigger by our action. It's not yet here. An event is not yet here when no one has tried to obtain it. Okay? There is no intrinsic existence of events, not even events. The existence of events is relative to our action that triggers them. Okay? So a probability, they say, is not a statement about what is the case, but about what one can reasonably expect to be the case on the day we do the experiment. So you see how much of modesty there is in this interpretation. There is retreat on any claim of saying something about the world. No view of the world. Relinquishment of views. Okay? So, precisely, is this quantum Bayesian one more view of the world or not? I told you no, but maybe we can follow a little bit more of what Chris Fuchs, one of the main authors of this idea, says. According to Chris Fuchs, quantum mechanics is a user's manual for each of us. It's not a description of the world. It's a description of how to behave where we are and when we want to act in this world. And also, we have to understand, if it's true that indeed quantum physics cannot be read as a view of the world, then what is the world to prohibit any representation of it? So this is the metaphysical part of cubism. An attempt to elaborate a metaphysical view of the reason why there is no view, or the reason why there can be no view. So if you are Madhyamaka, probably you would suspend even that. But since they are not, they want to understand how is it that you can really not obtain a view of the world by means of quantum mechanics. Maybe the world is done in such a way that this explains why we cannot get a view. Also, other ideas. You remember yesterday I spoke of laws of nature, and I told you that some people like Bas van Fraassen said, no, there is no law of nature. There are laws of the model we use in order to guide us in nature. And it's exactly what the people of cubism say. There are no laws of nature, no intrinsic laws of nature, but we have evolved tools to navigate nature, to survive in it. And the laws of quantum mechanics is not a law of nature, according to them. It's a law of how to predict observations and how to use them for technological sake. Nothing more. So, summary of cubism. According to Fuchs, a quantum state, so-called quantum state. Now you know that psi has to be interpreted to be said a quantum state. A quantum state doesn't represent reality, but an agent's probability assignment reflecting her degrees of belief about the future. Does quantum physics give explanations? You know that scientists want explanations. They want to explain why such event happened, why is the moon receding from the Earth, and so on and so on. Quantum mechanics doesn't explain why things happen, but it explains why, in order to be coherent, the experimenter should assign probability, P. So maybe you can be dissatisfied with that. You could say, oh gosh, I would like more than that. I would like that, quantum mechanics explains me the world, and it explains why I should choose this or that probabilities to orient myself in the observations I do by acting in the world. Very different, you see? Less, but at least it gives no strange feature and no paradox, which is already an important result. Now, another idea that is very important in quantum mechanics and that is very related to that, it's that quantum physics is about relations between facts, relations between us and what we try to explore, not about absolute properties or absolute existence. So, in fact, this idea that science is about relations rather than intrinsic properties or intrinsic existence is, in fact, a very old tendency. It has started since the time of Copernicus, at least. I told you about the loop that the planet Mars is doing on the sky during the year, and people wanted to account for this fact. The explanation of Ptolemy, I told you yesterday, but is that in fact the planet is rotating around the Earth, but also it has a little circle in addition to the big circle, and it's undergoing a little circle around this point on the big circle. And this explains why there are loops. So, this explanation is an absolute explanation. Why? Because it explains a fact by means of an intrinsic property of the motion of the planet. The motion of a planet is such that you get this loop-like appearance. Now comes Copernicus, and what he said is, no, Mars doesn't do this complex motion around the Earth. In fact, Mars rotates not around the Earth, but around the Sun. And the Earth also rotates around the Sun. And then how do you account for this loop in the new model? Well, you have to account not for the absolute properties of mass, of the motion of mass, but you have to look at the relation between the motion of mass on the upper orbit and the motion of the Earth on the lower orbit. So the Earth is on the lower orbit, Mars is on the upper orbit. Now you see that Mars is going more slowly than the Earth. And this explains why it seems it recedes. It seems it's doing this loop. It seems to us, because we are linked on the Earth, to the Earth, and in relation to us, it appears that Mars is doing a loop-like motion. In relation to us, that's the key point, not in the absolute. So, at the dawn of science is also the dawn of relative properties as opposed to absolute properties. And the more you go in the history of science, the more you have relativity principles, relational observables, and the less you have absolute observables. Quantum physics is just I would say, the ultimate accomplishment of this tendency. But before, there was Einstein's theory of relativity. Einstein's theory of relativity was a very powerful move in this direction, saying, no, positions, times, and so on are all relative. They are not absolute properties of things. But in quantum physics, not only position and time, but all properties are relative. All properties, including mass. Maybe you know, before, at the beginning of quantum mechanics, people believed that mass was an absolute property. But now we know that mass, the mass of particle, is obtained as the result of a relation between what we call two particles. The particle itself, for instance, an electron, and the so-called Higgs particle. So the effect of drag of an electron inside a sea of Higgs bosons or Higgs particles accounts for the apparent mass of the electron. So the mass of an electron is a relational feature. Now, of course, in order to express this relational feature, namely the mass of the electron that is generated by the relation of the electron with the Higgs particles, I had to use a vocabulary of particles, as if electrons and Higgs particles were intrinsically existent. So I have to correct again this language and say, oh, beware. Electrons are not inherently existent. They are just states of excitation that we observe on a certain field in certain circumstances when we do something. And the same for the so-called Higgs boson or Higgs particle. The Higgs particle is a resonance of a field that is observed only if an observation is made. So, okay, you see relativity throughout. No more intrinsic properties. So in the history, what you find is this. For instance, Richard Feynman, a famous American physicist, said, nobody understands quantum mechanics. Why? You understand why now. Because no view of the world that fits with quantum mechanics is without paradox, difficulty, or incoherence. So it looks like we don't understand the quantum mechanics. But we understand quantum mechanics if we change our concept of understanding and don't want quantum mechanics to show you what is the world, but just show you how you do something in the world. So, and it's exactly what Niels Bohr said very early in history. He said, in order to understand quantum mechanics, we may have to learn what the word understanding really means. We have to change our standards of understanding. If understanding means trying to figure out what the world is according to quantum mechanics, then failure. But if we try to understand why it is not possible to give such a picture of the world, then maybe we can get a new kind of understanding. And the reason that was given why we could not get a completely coherent picture of the world independent of us is precisely that the world is not independent of us. And Niels Bohr said that in 1930. We are both onlookers and actors in the great drama of existence. We participate in it. We are members of it. We cannot disentangle ourselves from the world we want to explain. And therefore, we cannot fully explain it because we are part of the explanation of what is to be explained. Heisenberg also, quantum theory provides us not with an image of nature, but an image of our relations with nature. So if we understand that, namely that there are relations throughout, then we can suddenly be clear about everything that looks difficult in quantum mechanics. Of course, still, you know, when Bohr and Heisenberg were so lucid at the beginning of the history of quantum mechanics, many people adopted their views. And then they said, no, these views are too disappointing. We want to know more. We think that quantum mechanics tells us or can tell us something about the true intrinsic nature of the world. And so a new trend was born in the late 50s, then 60s, till the 90s, the so-called trend of trying to find a so-called realistic interpretation of quantum mechanics. Okay, so this attitude is tantamount to complain that knowledge could be only relational, because in this case one fears groundlessness and one hopes that future science will renew the old dream of Western science, namely to capture the world by reason, the world as it is independently of us by reason. But, you know, this complaint has not had good results. For 40 years, people have tried desperately to get a good, realistic interpretation of quantum mechanics without universally accepted success. So the other possibility is to accept what Bohr and Heisenberg has said 70 years ago, and to accept that indeed we are so entangled with the world that we have to accept that we will not have a full picture of what the world is independently of us. So here I quote another French author, Blaise Pascal, of the 17th century. What will man do, he said, but perceive appearances from the middle of things, not knowing either their beginning or their end? So since we are so entangled into the world, we can only be in the middle of things and trying to get appearances of it without knowing the beginning or the end of things, namely the nature of things. Now, if we accept that, I told you, is not something to be complained. Why? Because suddenly we reach full clarity, full understanding, in the new sense of understanding of what is quantum physics. So I will now list 5 paradoxes of quantum mechanics, 5 of the so-called paradoxes of quantum mechanics, and show that they are no longer paradoxes as soon as you have adopted the new attitude, namely accepting that knowledge is only about relations and not trying to get a picture of the world out of quantum mechanics. Okay, so let's see the famous experiment of Schrödinger's cat. Of course, who has heard of Schrödinger's cat paradox? Yeah, so only half of you, which is already not too bad, but that means that I have to explain carefully. If not, some people will not understand at all. So here is this picture shows the experiment. It's a thought experiment. It's a thought experiment. And here you have the pictures of Schrödinger and Niels Bohr who are observing the experiment. So the experiment is this one. First, at the extreme left, you have a piece of radioactive material. And this piece of radioactive material has probability 1/2 to disintegrate during 1 hour, the hour of the experiment. Okay, in quantum physics, one ascribes a state to this piece of radioactive material with a probability 1/2 to disintegrate in 1 hour. We say that the state is a superposition between being disintegrated and not being disintegrated, with probability of 1/2 of each alternative. And Dirac, famous British physicist, said, so this piece of material will have properties that are in some vague way intermediate between those of the two original states. So when you try to take psi seriously, namely as the state of the radioactive material, you should say that the state is indeterminate. It's intermediate between the two well-defined states, namely intermediate between being disintegrated and not being disintegrated. Okay? Okay, now, but this is only just the beginning of the experiment. Now, the radioactive material, when it disintegrates, triggers a counter. And the counter triggers a recording in a computer. And the computer, which is a robot, by the way, with an arm and a hammer, when it's activated, will throw the hammer on a bottle of poison. And if it throws the hammer on a bottle of poison, then poor cat will be killed. Okay. But, and first of all, of course, maybe you remember that sequence when I was explaining the cat paradox to His Holiness, and he was a little bit annoyed by this experiment, and I had to explain that this is only a thought experiment, it's not a real one. So the problem is that since the piece of radioactive material is in a state of superposition, then the counter, the computer, the bottle of poison, and even the cat will become in a state of superposition. Okay? So, problem. How a cat be half alive and half dead? That's very strange. This is Schrödinger's cat paradox. And the cat paradox becomes even more stringent when you realize that if you open the door of the lab and you look in it, you will see a cat that is either alive or dead, but not both. Not a little bit dead and a little bit alive. It will be either one or the other. It's impossible to observe anything else. So people say, oh, maybe it's the act of observing that has killed the cat. Who knows? Okay? So this is the paradox. How can just the act of staring at it kill the cat? That looks very strange. Now, let's look at the sentences and the words that are used to formulate the paradox. Maybe, in fact, the paradox is in the words we use. The word state, for instance. State of the cat. The state of the cat is half dead and half alive. So the sentence here is, after Schrödinger's preparation, this one, the system atom plus cat is in a superposed state, half alive and half dead. Okay? But the second sentence is that one finds that the cat is either in the state alive or in the state dead. But now, is the word state means the same in the first sentence and in the second one? In the second one, the word state means the state we observe, the state of the cat as it is seen by us. But here, we use the word state in a completely new manner in the sentence 1. We use the word state for a symbol that is a generator of probabilities of observing either the state, or either the cat dead or the cat alive. So the word state is used in two different meanings. And the paradox arises from the fact that we believe that the word state means the same between the sentence 1 and the sentence 2. If we understand that the meaning of the word state is completely different in the sentence 1, then the paradox disappears. So the question is, should we really say that psi is the state of the cat? Or should we say just that psi is a generator of probabilities for finding the cat in a certain state? Okay? If we say the second point, then no paradox. Okay? So you see, just changing the meaning of psi eliminates the paradox. Much more can be said about that. I can tell you, in order to convince people of that, because it's very simple, in fact. I hope everyone can understand that, because it's very, very simple. Instead, people have used, tremendous mathematics to try to solve this paradox with no success. So when they are said, oh, you just have to think about the meaning of the word state, and the paradox disappears, they are a little bit annoyed. Because they said, we have spent so many years to calculate and understand and so on. And in fact, the solution was very simple. It was philosophical, not mathematical. So in order to convince them of that, some work has to be done, and some work has been done by people like Chris Fuchs and even philosophers. Now, second paradox. Okay, how is it possible that something is both wave and particle? Of course, you can have a wave guiding a particle, as we have seen in the film, for instance. But what people say usually is that the things themselves are both particles and waves. Particles are very narrow, very located. Waves are extended everywhere. So how is it possible? Einstein, in 1911, when he was already thinking of this solution for the photon, said, this combination is impossible. But, he added, but God seems to have found a trick. He seems to have found a trick. Okay, so he didn't really understand how it is possible to combine the nature of a particle and the nature of a wave, but apparently nature works like that. Why is it that people believe that the world behaves like that? See the pictures below. When, there is the famous double slit experiment in which you send photons, you send light, in fact, across a screen that have two slits. And the rest of the screen is metal, so opaque to light. Then what you observe at first is spots. Spots on the screen, spots going here and there without apparent order, apparently random. Okay? And we say, oh, there are spots on the screen, so they are particles, because they are little spots, little dots. Okay? And the trace of a particle should be a little dot. Now, when you send more and more light, you see clusters of dots. And then the cluster of dots organize in stripes. And then you see only stripes. The stripes are called an interference pattern. Interference pattern. But how can you account for the stripes? How can you account for the interference pattern? Precisely by saying that there was a wave that was interfering with itself. Namely, the wave that goes through one slit makes interference with the wave that goes through the other slit. And that's why there are interference patterns. So now we are with the paradox. We have things that behave as particles, and yet they also behave as waves. How is it possible that they combine? Apart from the little model of drop jumping on the vibrating water, of course, which is just a model. Don't forget it. Well, maybe, either you say, I will try very hardly to combine wave and particles until they really fuse together, or you wonder about your reasoning. Why did I say this is a wave? Why? Because there was interference pattern. And because I wanted to explain the interference pattern. And because when you have a wave, you have interference patterns. Waves entails interference pattern. Good. But the fact that waves entail interference pattern, does it allow you to say that interference pattern entails waves? I'm sure you have done some logic. This is something that everyone does, especially in Tibetan schools. If A entails B, does it mean that B entails A? No. Okay, it's very clear. So it's absolutely amazing that 100 years of the best physicists have fallen into this trap, very elementary trap. The fact that waves imply interference doesn't mean that interference implies waves. Okay? Interference can be explained by over models. And there are models that explain interference patterns without waves. There are. I have several in mind. One of them is that there is a transfer of momentum between particles and the plates that have the interference pattern. Sorry, that have the slits. So at the edge of the slit, there is exchange of momentum, and then these kicks that are given by the edges of the slits disturb the motion of the photons and make a distribution that is similar to the one that would be obtained if a wave existed. Namely, these photons behave as if they were waves, but they don't. This doesn't mean that they are waves intrinsically. Okay. Also, there has been a wonderful theorem that says that the theory applying to phenomena that are relative to mutually exclusive contexts predict wave-like distributions of the phenomena. That means, well, this is a little bit abstract, but just to tell you the gist of the idea. If a phenomenon doesn't occur by itself, intrinsically, but in relation to the apparatus, for instance, the apparatus of the two slits, then you can derive mathematically that it will have a wave-like behavior. Wave-like, not wave, okay? So interference pattern can be explained by many alternative models, but it can also be explained by a universal model, which is just a model of interdependence, okay? The fact that phenomena are dependent on the circumstance of their appearance implies wave-like behavior. Okay? So you would say, I just try to pack again the conclusion. Interdependence implies wave-like behavior. Amazing, isn't it? I will skip on EPR correlation, but I will go to the problem of the existence of particles. The concept of particle is something that has been used currently in the vocabulary of the physicists who do quantum physics. But they know that there is a problem with it. For instance, when you do quantum statistics, namely you count the particles in various states in which they can be, you count them, you count many of them. It's called quantum statistics. Then you find that in order to get the good results, the good observed results, you have to assume that these particles are indistinguishable. Namely, they have no individuality. They have no identity. So, and Schrödinger was aware of that. And he said, what is a particle that has no identity? A particle that has no individual identity cannot be a being, an entity in ordinary sense. And there is even a slogan by an American philosopher called Quine. Quine said, there is no entity without identity. So this is, this is a rhyme, so it's beautiful because it sounds well. No entity without identity. If you can always lose track of something and this thing reappears here and there without you being able to connect this appearance at this point to this appearance at that point, then where is the particle? Is there a particle at all or just spots? Spots, dispersed spots. Schrödinger thought that the second case applied. There are no particles, in fact, only spots. And he said particles in the old naive sense do not exist. And also a more recent physicist, Joost, who said particles do not exist. And I even remember one of my colleagues who was a specialist of particle physics and who laughed and said, I am a specialist of a discipline with no object because particles do not exist. And particles, at least in the naive sense, do not exist. Namely, there are spots. We see spots on screens. We see tracks with discontinuous dots and so on. And because we have the old metaphysical picture of the West, namely substances, permanent beings that are solid and so on, then we say these dots belong to a single particle. But it is just our view that is like that. It's not a particle. Particle, we don't know where it is. According to quantum field theory, it's even more stringent. I told you that particles in quantum field theory cannot be said to be continuous beings, but just discontinuous states of excitation of a field. And this state of excitation of the field is also relative to the ability for us to observe it. Okay? So the particles are relative to the activation device, the device that is used to observe this field. And their number is unobservable. Namely, their number is relative to the type of or to the state of the apparatus you use in order to observe them. If you have a steady apparatus, an apparatus that doesn't move, then you will observe, say, zero particle in the box. But when the device accelerates, then suddenly, click, 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 you observe plenty of something that you call particles. So the number of particles is relative to the state of the device that is used to detect them. Where are the particles? They are only relative phenomena, relative observables, not absolute intrinsic existent. And my colleagues, Jean-Marc Lévy-Leblond and Bernard d'Espagna, said, therefore, we could say that particles have the mode of existence of a rainbow, not of a drop. Because a rainbow is not something intrinsically existent. It exists in relation between three items: sun, drops, and observers. So the rainbow doesn't exist intrinsically. The same for the particles. They are appearances, but they exist relatively to the mode of observation. Finally, I will come to indeterminism. So, maybe you know that the so-called indeterminacy of the trajectory of the quantum particles have been explained by the concept of disturbance. One says one cannot tell what is the trajectory of a particle because when one wants to observe the trajectory of a particle, one must send, say, a photon on these particles. The photon bounces on the particles. The information that is obtained by the photon is retrieved in a telescope or a microscope. And by way of this photon, we can know what is the position and the velocity of the electron here. Okay? But each time we do that, each time we try to know the position and velocity of the electron by way of sending a photon, the photon bounces on the electron and disturbs the electron. Therefore, the trajectory is disturbed by the very fact of observing it. And therefore, there is uncertainty about the position and velocity. So this is the usual way people explain things. But there are two possible consequences. Either you say, okay, the electron is an intrinsically existent being with an intrinsically existing trajectory, and unfortunately the photon bounces on it and it disturbs it, and we cannot really know what is the real intrinsic trajectory of the electron. But the problem is that there is no way to compare this knowledge we have obtained by disturbing the electron with another knowledge that would be ideally obtained by not disturbing the electron. So we cannot really know what is the real trajectory of the electron if we had not observed it and therefore disturbed it. Impossible. There is no way, no physical way. In principle, there is no way. Not in practice only, in principle. So is it cogent to say that the electron has a trajectory, but unfortunately we don't know which one? Or should we rather say, since there is in principle no way to know the trajectory of the electron, then we should say that there is no intrinsic trajectory of the electron, but only some elements of knowledge we get by way of observing. Okay? So this is Bohr who said the second thing. He said, in fact, quantum phenomena are indivisible. We cannot disentangle what comes from the electron and what comes from the disturbance we did by sending it a photon. So it is meaningless to speak of the intrinsic trajectory of the electron. And we have seen that it's meaningless to speak of the intrinsic existence of the electron. So here again, we land into something that is very, much less, say, metaphysical, much less view than usually. There has been also a theorem that shows that in the case in which you cannot disentangle the values, the properties of the objects from the act of observing, then you have indeterminacy. Okay? So I conclude, just for this morning, I conclude that for indeterminism, the reason why there is indeterminism is not that nature is indeterminate. It's not that we ignore a nature that is determinate. It's that we are completely entangled in this nature that we want to know. That there is not the being of nature on the one side and the being of us on the other side, but there is interbeing. Okay? Very simple. So I remember His Holiness asked, so how can you cope with this issue of causality? Can you say that quantum mechanics has demonstrated the absence of causality? I said, and he was, of course, very unhappy about that. he loves causality. And I say, no, indeed, you are right. Quantum mechanics has not proved that causality doesn't work. It just has proved that causality is relative to our intervention. That we are part of the causes. And therefore, we cannot know all the causes because we are part of the causes. Therefore, there are not absolute causes, but relative causes. When I said that, he was really happy because you know, even the concept of cause is criticized in Nagarjuna. It's criticized as absolute causality, and it's accepted in terms of interdependence, not in terms of absolute determinant causality. So I think this kind of conclusion is very easy to draw from a careful reflection on some theorems of quantum mechanics. So it's not, here again, it's not artificial. Look, this connection between contextuality and acausality, apparent acausality, is not something that I'm saying just like that. It's a theorem that has been demonstrated in the frame of the quantum theory of probability. So it's something that is really proved, you know. So I think we should stop at that point.